Welcome to Get Educare. In this video, I will explain the construction of transformer. The basic parts in any transformer are core and winding or coil. Now, this is the core of any transformer. This vertical portion is called limb or leg, and this is called yoke. The function of this core is to provide a path for passing of magnetic flux. That means flux will passes through the core of the transformer. The core is made of silicon steel. The percentage of silicon in silicon steel is generally 4 to 5%. Now, as we know, the phi flux equal to mmf by reluctance. That means phi equal to n into I mu ampere turns by reluctance. For production of required flux, if the reluctance is less, then the magnetizing current required in the transformer for production of required flux will also be less. As a result, the operating power factor of transformer will also high. How the magnetizing current is correlated with the operating power factor of transformer, I will explain in my coming videos, mostly in the equivalent circuit of a transformer. Okay, just for this time being, you remember that if the magnetizing current is very high, then transformer operates at low power factor. That's why our basic target is to make the magnetizing current I mu as minimum as possible. Now, the advantages of silicon and steel. Both silicon and steel are good magnetic material. Due to high magnetic material ferromagnetic property, the reluctance will be less. As a result, the magnetizing current required for production of required flux will be less and transformer operating power factor will be high. Number 2, the steel has a good mechanical property. It provides the mechanical strength of the transformer. Steel has a low hysteresis coefficient. As a result, the hysteresis loss of the transformer will be less. And again, the resistivity of silicon is high. Resistivity rho is high. As a result, the eddy current loss of the transformer will be less. In the loss chapter, we will explain how the hysteresis coefficient is related with the hysteresis loss and resistivity of the core is related to the eddy current loss. Therefore, you try to follow my all the videos. Now, second portion of transformer construction is the winding or coil. Generally, we need two winding. One is primary winding and another is the secondary winding. This primary winding, this is the secondary winding. As we explained earlier, the winding with less number of turns, suppose N1 is the LB winding, and the winding with higher number of turns N2 is called HB winding. Here N1 is less than N2. If N1 is less than N2, then it will be LB winding, and this is HB winding. If N1 greater than N2, this winding, primary winding will be the HB winding and secondary winding will be the LV winding. Now that means here this is the LV low voltage, here N2 that is the HB high voltage, but here is the HB, N1 is the HB high voltage and N2 is the low voltage HB. Now as we know, if we apply a AC voltage to the primary winding and magnetizing current will be drawn from the supply. Due to this magnetizing current, a flux will be produced which is alternating in nature, changes, that means changes with time. This flux links with primary as well as secondary, and this primary winding feel the flux which is passing the winding changes with time. Therefore, according to Lenz's law, an EMF will be induced into the primary winding. Similarly, whenever the secondary winding see by feel that the flux which is passing through the secondary winding also changes with time, therefore an EMF will be induced into the secondary winding E2. At the same time, the transformer core, all the transformer core material also feel that the flux which is passing through the transformer core it changes with time. Therefore, an localized EMF will be induced in the transformer core itself. This localized EMF is called eddy induced EMF. Eddy induced EMF. This eddy induced EMF we don't get in output terminal. In transformer core itself, due to eddy induced EMF, a current will circulate in the transformer core. This current is called eddy current II. Due to this eddy current, a power loss will be happened in the transformer core, and this is called eddy current loss. Due to eddy current loss, the transformer core is unnecessarily heated up, which is not desirable. So we need this eddy current loss as minimum as possible. Okay, eddy current loss, we can say eddy current loss W of E equal to I of I square into RC. What is the I? That is equal to eddy current RC is the resistance of core material.
V by RC, voltage by resistance equal to the current. Eddy current equal to voltage by resistance of the core material. If the resistance is high, core material resistance is high, then eddy current will be less. Therefore, power loss due to eddy current will be less. This is the eddy current loss. Recurrent loss will be less since the eddy current loss is the eddy current square into RC. RC is increasing, but eddy current is decreases with the power. Therefore, resultant eddy current loss will be decreases. As I told you earlier, therefore the resistance of the core should be as high as possible. Therefore, we use silicon so that the silicon has the high resistivity. Due to high resistivity, the core resistance will be high, eddy current will be less, eddy current loss will also be less.
Again, to reduce the eddy current loss, the lamination is done of the transformer core. So this is the solid core, and this is the laminated core. core. Here the laminated core is like a sliced bread. The every core element is made of small sheets of thin small sheets, and with the help of nut and bolt the all the sheets are joined. Okay. Now what is the advantages? The advantages is that due to this air gap between this sheet by laminations, the resistance RC will increase. Since RC will increase, eddy current will decrease. As I explained earlier, due to less eddy current loss will be also reduced.
For transformer core is not made of solid material. Is it made of laminated core, and the for a frequency of 50 Hz, the thickness of lamination of transformer T equal to 0.35 mm.
Another type of losses occurs in the winding of the transformer. If the current I is passes through the winding and the resistance of the winding is R, then the resistance loss will be I square R loss in the transformer core. This is called transformer winding. This is called copper loss. So copper loss equal to I square R loss. My main target is to reduce this copper loss. Suppose the current rating of the winding is 25 ampere. So I will use a conductor of higher diameter which can stand the 25 ampere. Single conductor which can passes through 25 ampere is called single strand wire. Instead of using one conductor of capacity 25 ampere, I can use 5 strands of 5 ampere each. This is 5 ampere, 5 ampere, 5 ampere. All can has a capacity of 5 ampere. Total is the 25 ampere. This is called multi-strand wire. The single wire of capacity 25 ampere is called single strand wire, and multiple of conductors have the same 25 ampere capacity is called multi-strand wire. In order to reduce the copper loss, we don't use this single strand wire, we use multi-strand wire. Why? The reason is that since the diameter is very high of single strand wire, due to higher diameter, a skin current passes through the surface of the conductor. This is called skin effect. Due to skin effect, the resistance R increases. Therefore, I square R loss also increases. But if we use the multi-strand wire, there is no skin effect, and the resistance of the winding is less and less I square R loss. Therefore, I use multi-strand wire. Thank you for watching this video. In the next video, I am going to explain the construction of core type and shell type transformer. Okay. With the help of Get Educare channel, I am going to upload every details topic of electrical engineering. If you like this video, please subscribe the channel and share to all of your friends. Thank you once again.